Booster 18 sat inside Megabase since May, 6 months with zero movement. Then November 19th arrived and SpaceX rolled out this massive V3 hardware to Massey test site. What suddenly changed? Welcome to Space Update 24 hours. The same day B-18 moved, Pad 2 received its QD arm. Raptor 3 engines are ready for installation. Static fire is scheduled for early December. This is the first true V3 booster hitting the test timeline. But here's what everyone's asking. Why did SpaceX wait 6 months, then explode into action overnight? Let's dive right in. Here's the reality. SpaceX blocked off a 4-hour window from midnight to 4 a.m. for B-18's transport. Road closures that long only happen when something massive is moving. The team didn't just roll this booster out on a whim. They prepared for weeks. A brand new V3 optimized booster stand arrived at Mega Bay days before the rollout. That's not coincidence. You don't move specialized hardware into position unless you know exactly when you'll need it. So what was SpaceX waiting for all those months? The answer lies in what happened after Flight 11. Before that mission, Starbase looked sluggish. Crews working at half speed, hardware sitting idle, progress barely visible. Then Flight 11 launched and everything shifted. It's like someone flipped a switch. Suddenly, Starbase transformed into a completely different operation. Multiple teams working simultaneously. New equipment arriving daily. And B-18 finally got its marching orders. But moving the booster was just step one. Once B-18 reached the Massey test site, the real validation work began. This is where V3 hardware either proves itself or exposes fatal flaws. The beauty of Massey? No road closures needed. SpaceX can tank propellant, run pressure tests, and cycle systems 24/7 without asking permission. For a company moving this fast, that flexibility is everything. The upgraded quick disconnect system installed in August is specifically engineered for V3 architecture. Previous boosters needed constant adjustments during fueling. Engineers would monitor valve behavior, tweak pressure settings, compensate for thermal expansion issues. B-18 doesn't need that babysitting. The QD feeds propellant cleanly, holds pressure consistently, and handles cryogenic temperatures without the drama earlier versions created. That's the difference between prototype hardware and production-ready systems. The testing protocol is straightforward but brutal. Fill the methane tank first, monitor pressure stability, check every weld, every seal, every connection point for leaks. Watch how the steel responds to extreme cold. Liquid methane sits at minus 161 degrees Celsius. Any weakness in the material shows up immediately. Then drain and repeat the process with the oxygen tank at minus 183 degrees Celsius. Each tank gets individual validation before the combined test. That final test, both tanks loaded simultaneously, is where hidden problems surface. The combined thermal stress, the weight distribution, the pressure dynamics when both systems operate together. That's when engineers discover if their calculations actually work in reality. If B-18 passes this phase within 2 or 3 days, as planned, it heads back to Mega Bay 2 for the next milestone. What comes next? Raptor 3 installation. These engines represent the most significant upgrade in the entire V3 package. They're simpler, fewer parts, easier to manufacture. They're stronger, higher thrust, better reliability margins. And they're designed for mass production at a scale SpaceX never achieved with Raptor 2. Each engine goes through individual acceptance testing before mounting. Once all 33 Raptors are bolted to B-18, the booster moves to Pad 2 for static fire. If the current timeline holds, that static fire could happen before Christmas. But there's a bigger story developing across Starbase that most coverage is completely missing. Pad 2 looked unfinished for months. The tower stood there, mostly complete, but missing critical hardware. The ship quick disconnect arm, the massive mechanical system that fuels and supports the upper stage, wasn't there. That changed November 19th, the same morning B-18 rolled out. Crews transported the QD arm from the Sanchez construction site to Pad 2 and positioned it for crane installation. The timing isn't random. SpaceX doesn't move major hardware without a plan. B-18 reaches Massey for testing. The QD arm arrives at Pad 2, Raptor 3 engines are ready for integration. Everything is synchronized. This is what operational maturity looks like. Multiple critical paths advancing in parallel, each dependent on the others, all hitting their marks within hours of each other. Meanwhile, the flame trench beneath Pad 2 has been tested multiple times recently. Water deluge systems activated, pressure dynamics measured, heat resistance validated. Once the upper integration hardware is in place and aligned, Pad 2 becomes fully operational, not just for B-18's static fire, but for actual launch operations. SpaceX is building redundancy into their launch infrastructure. 2 pads, 2 complete systems, double the launch capacity. Now here's where the conversation gets interesting. After Blue Origin's second New Glenn launch, social media exploded with comparisons. Some people genuinely claim Blue Origin is now competing with SpaceX at the same level. Others suggested Blue Origin might even be performing better. The second New Glenn flight was impressive, no question. The rocket ascended smoothly. B4 engines performed significantly better than Flight 1. And the booster actually landed on the ship in the Atlantic. That's a real achievement for a first-generation heavy-lift vehicle. But let's examine the full context. New Glenn has experienced more than 3 major delays, plus multiple scrubs just attempting the second launch. The first flight was technically successful, but the booster didn't land. Engineers identified issues with guidance systems and engine throttle transitions. Even the second launch, while successful, didn't achieve the landing precision Falcon 9 demonstrates on literally every routine mission. Those are just the visible problems. The deeper issue is time. Blue Origin started New Glenn development in 2011. 14 years later, they have 2 flights total. During that same period, SpaceX didn't just develop Falcon 9, they built an entire orbital transportation empire. While Blue Origin celebrates their second flight, SpaceX maintains a launch cadence that seems physically impossible until you watch it happen. The numbers tell the story. In 2023, SpaceX completed 96 orbital launches, a world record. In 2024, they launched 132 times. That's more missions than any country on Earth had ever achieved, let alone a private company. Now in 2025, they're ahead of their own pace. By mid-November, SpaceX had already crossed 110 missions, tracking toward an estimated 140 to 150 total flights by year's end. Compare that to Blue Origin's record. 2023, 0 orbital launches. 2024, 1 New Glenn test flight. 2025 so far, 1 more mission. 2 total flights while SpaceX launched over 250 times. This isn't a rivalry, it's 2 completely different operational categories. The economics make the gap even more obvious. A standard Falcon 9 launch costs about $67 million. But because SpaceX reuses boosters 15 to 20 times, the real internal cost drops dramatically. Gwynne Shotwell has stated publicly that a reused booster brings marginal launch costs down to $15 to $20 million. Divide that by 22 tons to low Earth orbit, and you're paying under $1,000 per kilogram. That's the cheapest access to space in human history. Falcon Heavy destroys the competition even harder. An expendable Falcon Heavy launch runs around $97 million. Reusable configuration with maximum performance? About $150 million. For 63 tons to LEO, that delivers heavy lift capability at prices nobody else can touch. Crew Dragon's numbers are even more telling. NASA pays SpaceX roughly $55 million per seat for certified crew missions. That includes full training, pressure suits, safety systems, mission planning, and all required oversight. Compare that to what NASA paid Russia for Soyuz seats after the shuttle retired. Sometimes $90 million, occasionally over $100 million per person, for a capsule designed in the 1960s. Now look at Boeing's Starliner. Even ignoring all the delays and system failures, each seat costs NASA around $90 million. That's nearly double what Dragon charges for a vehicle that still can't complete a clean mission. The performance gap isn't just about technology, it's about execution, reliability, and actual operational capability. This is why B-18's rollout matters beyond just one booster moving to a test site. It represents SpaceX's next evolution, from rapid iteration to industrial-scale production. V3 isn't just bigger hardware, it's a complete system redesign built for manufacturing volume that makes current production rates look slow. So what does all of this actually mean? B18's rollout isn't just about one booster finally leaving Megabay after 6 months. It's the visible proof that SpaceX has entered a completely new phase. V3 hardware isn't experimental anymore. It's production ready. The upgraded quick disconnect systems, the Raptor 3 engines, the synchronized infrastructure built out across Starbase. These aren't test articles. This is SpaceX transitioning from rapid prototyping to industrial manufacturing. While other companies celebrate their second flight, SpaceX is already building the system that will launch 200 plus times per year. That's the difference. Blue Origin landed a booster and the world applauded. SpaceX lands boosters so routinely that nobody even notices anymore unless something goes wrong. That's not arrogance. That's operational maturity. The next few weeks will define how fast V3 becomes reality. If B18 passes cryogenic testing, gets its Raptor 3 engines installed, and completes static fire before year's end, we're looking at a potential V3 launch in early 2026. That timeline seemed impossible 6 months ago. Now, it's the expected schedule. This is why following Starbase development matters. Every hardware movement, every test campaign, every infrastructure upgrade tells you where the entire space industry is heading. And right now, it's heading toward capabilities that sounded like science fiction just 5 years ago. What do you think? Will B18 complete static fire before Christmas, or will SpaceX hit unexpected delays? Drop your predictions in the comments below. If this breakdown helped you understand what's really happening at Starbase, hit that like button and share this with anyone following space development. And subscribe to Space Update 24 hours so you don't miss the static fire coverage when it happens. We'll be tracking every step. Thanks for watching, and I'll see you in the next one.